My name is HyungBin, a graduate student from Kookmin University, South Korea. And today I will talk about my research, generative intrusion detection and prevention on data streams. Shortly, kids. So there are 4 types of intrusion detection, such as manual comparison, signature generation, ML-based supervised, and unsupervised learning. We observe that none of them can satisfy high accuracy, automation, and zero-day attack mitigation at the same time. This motivates us to study GIFs that can generate signature groups automatically to mitigate a special type of zero-day attack with high accuracy. Because GIF provides signature groups, an evidence is also provided to security practitioners. This is a practical usage, while ML-based approaches just detect attacks as a black box model. Some previous work can generate signatures from the network packet against a zero-day attack. However, all of them work only when most packets are from attackers with very similar packet content. So in this slide, the attack ratio is up to 80%. When the attack ratio is so high, we are able to identify frequent suspicious signatures by selecting the most frequent substring from a simple hash table. However, our previous work failed to identify suspicious signatures in dataset when the attack ratio is low. Although the attacker sent a similar content repeatedly, 20% in this slide, their total amount is literally much smaller than that of normal traffic. We will call this problem as a persistent zero-day attacks. Previous work cannot generate proper attack signatures because the normal payloads appear most frequently. To solve this problem, we developed GIFs that can identify attack payloads as a big group, even when the group rate was as small as 0.001. This is a big improvement because previous schemes work fine, only the attack ratio is very high. Here is an overall process of GIFs that can generate signature groups with limited computing resource for streaming data. So when the streaming data are continuously provided, we first identify big groups using two compounds called MV2 and JIG. Then the signature groups are generated by SG2 and AW compound. So in the MV2 compound, we vectorize the payload based on MinHash to identify the big group quickly. We first transform the packet payload into chunks as in A. In this paper, we use a chunking algorithm called AE chunking for that. Then we use MinHash to generate the bitmap to encode the packet payload. MinHash is an algorithm that compresses data using k-distant hash functions so that the Jakarta index can be estimated. Using the hash functions, we encode the payload as a bitmap vector. For example, we choose the minimum hash value for the first hash function of H0, 9 in this slide. Then the first index 1 is turned into 1. And we repeat this for all hash functions. Because of MinHash, we can perform vectorization independent of the number of chunks, as well as satisfying the property of Jakarta index. In the JIG compound, we want to determine whether the data belongs to a big group or not. However, we cannot use a live clustering algorithm because of the excessive increase in both of time and space complexity. Instead of using a heavy clustering algorithm, we summarize the similarity relationship among the streaming data into an integer array called MV for managed virtual vector. This env is initialized 0 as in this slide. And there is predefined threshold of theta j. In this case, when the first data D0 comes, we encode it into the MV. In this slide, 3 hash functions of the min hash determine the 3 positions that increase by 1 respectively. For the second data D1 comes, the min hash determines the 3 updated positions too. D2 and D3 are also provided. And when D4 comes, we can find that some counters become significantly greater than the others in MV. We will call these counters as big counters. In this slide, the criteria to become a big counter is mean plus 6 times sigma. If the ratio of the number of big counters to k is larger than a predefined threshold theta j, we say that a big group of D4 is identified. This means that we may have found a big group including D4 in terms of Jacobi index. Then we store D4 into a special space S. And when D5 comes, we find that the same big group is identified. Again, we find 2 big counters that satisfy the theta j condition and 6 sigma condition. Actually, we design an iterative unreliable retrieval algorithm called IORA to find big counters quickly. Now, S includes D4 and D5. In the check compound, we can identify big groups with a small fixed amount of memory and a constant number of hash operations. Next, in the SGD compound, we make cluster from S that includes the data belonging to big groups. Because we filtered out non-big group data in the check compound, the clustering over S can be finished very quickly. Then we generate the signature group for each cluster. We use the triple repeater algorithm THH to take common signatures for each cluster. Finally, AWL, the last compound, we generate those normal signatures that appear in most of the data. Because these signatures are often cost positives, we are able to subtract or whitelisting them from the attack group signatures. We experimented with 4 different datasets, simulated, IoT, IDS, and ISP. Each dataset consists of multiple ticket files. IoT23 and CIC-IDS 2017 are well-known public datasets available from the internet, while the ISP dataset was collected by a Korean ISP. We evaluated big group identification using simulated dataset and sequential group generation using the other 3 datasets. Here are the results of big group identification with the simulated dataset. Even when the group rate was as low as 0.01 and especially 0.001, very little memory and very few hash operations were used to achieve high accuracy. And here are the experiential results of sequential group generation with the IoT dataset. In the case of the blue boxes, the big groups within the dataset were identified, and the sequential groups were extracted so that the security expert could analyze them easily. For example, 3 signatures are generated as group signatures: phone, root, CAC mode from the IoT6. All of the group signatures contain substring that appeared only in attack package. And especially in the case of the IoT6, while other library schemes achieve a low F1 score because of false positives, GIFs can remove the false positives well. However, GIFs do not always work well for all datasets. In the case of the green box, the performance of GIFs and triple repeater was similar. This is because the IoT4 dataset has an extremely large number of identical attacks the 99% in fact. Therefore, both GIFs and triple were able to extract signatures well. And in the case of the red box, there is no relative content that can generate any signatures. So it prevents GIFs and other library schemes from working well based on frequency. Next, here are the experimental results with IDS datasets. GIFs can solve the first positive problems that other schemes cannot solve, resulting in GIFs achieving a high F1 score. As shown in the blue box, two suspicious strings are generated from the IDS1. For IDS1 and IDS7, GIFs not only generate object signature groups, but also resolve the first positive problems perfectly. However, GIFs and other schemes do not work at all for IDS5 dataset. This is because the dataset has many encrypted datasets based on secure shell. And additionally, in the case of the IDS8, there exists no relative content that can generate enable signatures too. Moving on to the result of the ISP dataset. The ISP dataset have high attack ratio relative to the other dataset. So library scheme, especially triple work as well as GIFs. However, GIFs is the best to identify big groups and generate signature groups. We observed that 3 datasets include enable signature groups respectively. We also measure time and memory usage, and thanks to the MV2NG compound, we are able to significantly reduce time and memory usage on a large dataset. In conclusion, we have presented a new generative IDS to mitigate persistent zero-day attacks using big group identification and signature group generation method. Although GIFs have such a limitation as encrypted data analysis or no repetitive content, we believe that GIFs can help security practitioners by automatically generating signature groups with only limited computing resources. Thank you for listening to my presentations.